we're going to try this and see how well I can do the PDF with the series. So here we go. So I apologize in advance if it's a little sporadic and learning how to make it move through here. Okay, so this unit is on bonding. It's actually a very important unit. A lot of questions, kind of like atomic structure on the last unit. A lot of theory questions show up on the AP exam, either in the free response or in the multiple choice questions themselves. What is a chemical bond? Okay, it's going to take us, this is going to be basically chapters, I think, 10 and 11 in your book. Okay, bonds, of course, are the attractive forces that hold groups of atoms together and makes them function in a unit. Okay, bonding relates to physical properties. So depending on what kind of bond you have, your physical properties such as melting point, hardness, all those kind of things are based on their bonding characteristics, okay? Whether you have an ionic or a covalent bond. The reason that things bond is, why do you think?
Electrons.
They want the lowest possible energy state, so the lowest possible potential energy. So bonds actually will, or atoms will actually release energies when they bond, okay? So it takes energy to break a bond because they don't want to, they're less stable. So atoms themselves are less stable than when they're bonded, okay? So it's going to actually release energy, okay? And that's actually a misconception among students sometimes, is they think that the energy is released, or it takes energy, how do I say this? I can't think how I want to say it, but it's like a misconception because you think it's stored energy, but actually it takes energy to break it. You got to put energy into the bond. Most people think it's stored energy because what did you learn in biology about ATP?
When it breaks, we get it.
Yeah, but it's not stored energy. It takes energy to break the bond, actually. So that's a little bit of a misconception from biology. So bond energy, obviously, is the energy required to break the bond. When we did thermochem, we talked about that bonds broken minus bonds formed. That's going to show up again because it takes energy to break the bond. You got to break them before you can form new ones. So the general types, we're going to have, let's see if I can move this up. We've got ionic bonds, of course, which are that electrostatic attraction between ions. What type of ions do we have? Positive and negative? Positive and negative, cations and anions. So they are attracted, the opposites attract kind of thing. It's usually produced by the reaction between a metal and a nonmetal. Not always. There are some nonmetal bonds based on their electronegativity difference that would be ionic. For instance, boron and fluorine would be an ionic bond, even though it's a metalloid and a nonmetal. They are the strongest of the chemical bonds, and that's why they have very high melting points. They are almost always in the solid state since their attractive force is so strong, and they're very close together. They form that crystal lattice structure. Okay. Covalents, of course, are shared. The sharing is very rarely 50-50. So when they share, we're either going to have polar bonds or nonpolar bonds, which we'll get to in a little bit. That should be a review from Chem 1. Y'all should at least remember nonpolar polar bonds, okay, which is different than the molecule, because you remember you can have a polar bond but have a nonpolar molecule, which we'll get into in a little bit. Coulomb's law is going to be used strictly to explain ionic bonds, okay, and that's where those charges come in the distance between the charges, okay. Because we're going to have a positive and a negative charge, what is your energy going to always be? Negative, okay? So negative sign on the energy once it's calculated, okay? Right there. Let's see. Not too bad so far. Valence electrons, remember, are your outermost S and P, and if you're in the transition metals, we'll be looking a little bit at those d orbitals, okay? Lewis dot structures, that's what you did today. The man that's responsible for that is G.N. Lewis. He was actually the first American chemist to receive the Nobel Prize. And you remember when we vaguely talked about acid bases in Chem 1, we had a very small definition about Lewis acid and bases. It's the same dude. He was very instrumental in some of our understandings of chemistry, but he was the one that came up with the Lewis structures. Emphasis on rare gas configurations, which they're calling rare gas. That's what we call as noble gases. And that is that stable S2, S6, or the octet. And remember, all of the noble gases follow the octet rule except for helium. How many does helium have? 2. Okay. And of course, octet means they have how many valence electrons? 8. Okay. There are some other exceptions to the octet. Rule. For instance, beryllium and boron will not have 8 around them. Boron will only get, how many do you think? Has 3 valence electrons. So how many do you think it can get when it shares its 3? 6. So the most that boron can get is 6. Anything below carbon is going to be under that octet rule. It's going to be less than. Okay. Carbon is the first one that can get 8. Okay. Chemical bond formation. So basically it's this. Okay. The way that they form is they have to reach that optimum magical distance at where they're overcoming the electron-electron repulsions and the proton-proton repulsions, because if they're too far apart, they're not attracted to each other. If they get too close together, the electrons repel each other and the protons repel each other. So there's that little sweet spot in the middle, or if like some people call it the Goldilocks spot, because it's just right. Okay, don't use that on a test. Don't say it's like just right, like Goldilocks. Don't say that on a test. These are generalizations to help you understand them. Okay. But don't write that on a test. Don't say an atom is willing to give away his electron. He does not have a will. It's not a person. Okay? But those are things we talk about, generalizations, to help you wrap your brain around it. Okay? That bond length is that optimum distance between the 2 nuclei, where the energy is at its minimum between the 2 nuclei. So if you look at this graph right here, you can see how they're too close right here. Here they're too far apart, and then right here where they're just right, the energy dips down because that's where the energy is a minimum. Okay? If the energy decreases, well, they call them van der Waals, but they're IMFs, intermolecular forces. Last year in Chem 1, we sometimes called them interparticle forces, but they're the forces between the particles. If your energy decrease is really large, then that's when you get a chemical bond. Okay? Any questions so far? We're all about getting that lower energy state. Nature always likes things in its lowest possible energy state. That's why we bond. Okay? Questions so far? Mostly seems to be a repeat from Chem 1 so far. Okay. There's a couple of different orbital bonding theories. First one we're going to talk about is orbital theory. And that's where your positives and negatives, you might want to kind of highlight that because they kind of get lost. The positives and negative electrons and positive nucleus of an atom change the spatial distribution of the other atom's electrons. Okay, so when they're individual, they have a certain wave function. When you put them together, it kind of changes that. We don't care much about the wave function. We just need to know that we have this new thing called a bond orbital. Because remember, if it's a covalent bond, their bonds are actually their orbitals are actually overlapping and becoming one. Unlike an ionic compound, which is positive negatives just held together by that electrostatic attraction, when they bond, they're actually overlapping their individual orbitals and kind of forming a new one. Okay, that's called the bond orbital. And remember, when we draw a bond, that represents 2 electrons, right? Okay. Your lone pair orbital is the ones that just belong to the individual atom. So when you draw a lone pair on there, say for when we're doing water and oxygen has its 2 lone pairs, those belong exclusively to that oxygen. However, because they're bonded, it kind of changes their spatial area around its individual than if it was by itself. Okay? So basically, this new orbital is built right here. From the 2 bonded, okay? Ionic bond, the bonding orbital is so strongly displaced that it's giving the electron away, okay? it's giving it. And then the covalent bond is more or less evenly distributed. If it's a nonpolar, it is exactly evenly distributed. They share equal, okay? If it's polar, there's an unequal distribution or an unequal sharing. Which one gets the electron more? Mohammed, which one gets the electron more in a nonpolar bond?
What do you mean by get it more?
It has greater custody of it. They're sharing an electron. It's nonpolar. One gets the electron to keep it more than the other one. Which one is it? Ben Kuo, who gets it more?
Like if it's non-polar, then they.
No, if it's polar, which element, if it's polar, which one gets to hang on to the electron more?
More electronegative.
The more electronegative, yes. The higher the electronegativity, the more it gets the electron. Because remember from trends, electronegativity is the ability to attract an electron. So if it has a high electronegativity, it gets to hold on to the electron more. Okay? This is a very important thing to recognize, and that is that when we're talking about bond characteristics, that most chemical bonds are somewhere between purely ionic and purely covalent. Okay? There really is no such thing as a purely ionic bond. It just has more ionic character. Okay? And I'll remind you that these still really are all just theories. We teach them as if, yes, this is exactly how it happens, and it's how we have to understand it, but it's a theory. Okay?
Okay, we can't look at it, but this is what all the evidence is pointing to.
This is what the evidence is
And we
pointing
haven't been
into.
able to disprove
Correct.
this, so
Correct. Okay? So it's all about the electronegativity when it comes to if it's ionic, polar, or nonpolar. Okay? So you have this chart in your notes. I can give you a better chart than this because I know you can't read it very well in your notes. Because when it prints out in color, we're not fancy enough to have, I can't get you colored notes. Okay? However, if you have a color printer at home and you want to print out colored notes because they're prettier and you can see them better, I can tell you where to go to get the notes. Or I can put them, don't know if I've put them up on Canvas. I need to. Okay? So, of course, fluorine is our most electronegative. We drilled that to you in first Chem 1. And then francium down here is the smallest. Okay? Why is fluorine the highest? Because it has the highest effective nuclear charge of all the elements, and it's got the smallest radius. So that's going to have the highest electronegativity. Okay? Whereas francium is got the largest effective nuclear charge and the largest radius, so it's further away. Okay? So how do I know what's the differences if it is ionic, polar, covalent, or whatnot? And that's this little chart down here that you need to just memorize. So write yourself a note to memorize. If the difference in electronegativity is greater than 1.67, then it is considered to be an ionic bond. If it's between 0.4 and 1.67, it's considered polar. And then anything less than 0.4 difference in electronegativity is nonpolar. And there's not a whole lot of nonpolar bonds out there. There's not that many. Why do you think?
because there's usually a difference in electronegativity.
Usually there's something that wants the electron more.
Well, not once.
Has a high, yeah. Those are generalities. Don't say once, but yeah. What are some nonpolar bonds that you know of right off the top of your head? H2O2. Your Brinkelhoffs, right?
Yeah.
Because anything bonded to itself is going to have a 0 electronegativity difference. So your Brinkelhoffs, which are bromine, iodine, nitrogen, chlorine, hydrogen, and oxygen, and fluorine. Okay? So that is something you're just going to have to memorize. Okay? Now, if you have to do that on a test, you'll either have an electronegativity chart, or on the AP exam, they'll give you like a little partial one. Then you do not have to memorize the electronegativity values. Other than you should know that fluorine is the greatest and francium is the least. There's 4 that are the most electronegative. You should know those, and those are going to be nitrogen, oxygen, fluorine, and chlorine. Those are your 4 highest electronegativity values. I have to take it off writing to be able to move it up. I'm getting it down. I'm not doing too bad for the first time with this. Okay, So we're going to order these bonds according to polarity. Okay, so let's do that. So hydrogen is going to be what? Non-polar for sure. So we're going to put NP under that. Okay, let's do the electronegativity difference between oxygen and hydrogen. Okay, let's just do this real quick so that we don't have to flip back and forth. Oxygen's value is 3.5. Can't make that be a 3. That's a horrible 3. Oxygen's value, what is the deal with the 3? I'm just going to leave it. Chlorine is 3.0. Hydrogen is 2.1. Sulfur is 2.5. And then, of course, fluorine is 4. So the hydrogen-oxygen bond, what would its electronegativity difference be? Well, I get 1.4. What would the chlorine-hydrogen bond be? Do mental math, guys. What's 3 minus 2.1? 0.9. The sulfur-hydrogen bond would be how much difference? 0.4. And then the fluorine-hydrogen bond? 4 minus 2.1. Math is hard.
Wait, what's the 2.1? Is that hydrogen?
That's hydrogen, yeah.
It's the polarity of hydrogen?
No, it's electronegativity values. These are their EN values up here. I just did it so we didn't have to keep flipping back and forth on the page. So what is it's according to polarity, I'm assuming it means increasing in polarity, okay? So what would be our first bond? The least polar. The hydrogen-hydrogen bond, which is going to be less in polarity than, what's the next one? The sulfur-hydrogen. Then the chlorine-hydrogen. And then the greatest, it would be, of course, you would expect the one with fluorine to be the greatest, right? Okay. When we get to acid and bases, you may remember from last year we have strong acids and strong bases. Hydrogen chloride or hydrochloric acid is a strong acid, but HF is not. Okay, remember it was one of the weak acids. The difference is their character. So HF is an ionic bond, so it's very strong, so it's not going to break apart very easily. Whereas HCl is a polar, so it breaks apart easier. That's why it's a strong acid and completely dissociates. But HF doesn't completely dissociate because it's such a strong ionic bond. So water doesn't have enough to dissociate it. Doesn't have enough oomph to dissociate it. Okay? Bond polarity and electronegativity plays a part. Okay? And of course we said that on the last page. Electronegativity ranges from 0 to 4.0. 0 would be, well no, actually they're talking about ranges, the electronegativity difference. So 0 would be when you have the diatomics. Their electronegativity differences would be 0. I don't know why they're saying it could range to 0.4 because to me your smallest and your lowest is 4 and 0.7. So to me it would be 3.3. But anyway. So this is kind of, you've seen probably this from Chem 1. What's the first one representing? Nonpolar, yeah. Because it's equally sharing. And then the next one would be polar covalent, and then this is ionic because it's an outright, here, take my electron. I don't need it. Okay? Okay, here's ionic bonding. A little bit further detail. The final result of an ionic bond, of course, is a solid, regular, it's very structured array of cations and anions that we call a crystal lattice. Here, this little diagram over here is kind of showing you the energy changes involved. You will see one of those diagrams on Friday when I am gone. You're going to do a POGL on crystal lattice to make sure you understand that. I'm going to be gone Thursday and Friday. Did I already tell you all that? Yeah, I have to go to a conference in downtown Houston, and Mr. Norbrotten is your sub.
Oh, great.
Yes.
Yeah, okay, so he's your sub. But here's where you're going to use Coulomb's law. We had that one question on the last test about K2O and calcium oxide, which one had the stronger lattice energy. This is where that would come into play from that kind of thing. The energy of attraction depends directly on the magnitude of the charges. Okay, this would be a good thing to highlight. I don't like my highlight color. It's not showing up very well. Oh, well, if I can't change it. Energy of attraction depends directly on the magnitude. Higher the charges, the greater the attractive energy. It is inversely on the distance. Okay? Inversely on the distance. Okay? So if I was to look at this and my distance was about the same, so let's just say I have a distance of 1, and I had something that had charges of a -2 and a +2, and charges of a +1 and a -1, which one would have the higher lattice energy? Plug in those numbers. I got, let's say I have, calcium and sulfur, and let's say I have sodium and chloride. Let's just pretend right now they're the same distance apart. Okay, which one of those would have a higher lattice energy? Because remember, you're going to plug in your negatives and positives right here. So what's your charge on calcium? And let's just going to pretend like it's 1 right now. And then that would be +1 and -1 over 1. Which one of those would have a higher charge, or higher lattice energy, or higher energy to break? Yeah, this one. Because it has higher charges. And that was where this right here depends on the magnitude of the charges. Okay? Does that make sense now? Okay. The larger the ion, the smaller the dissociation energy, distance. Okay? Ion attractions have a profound effect on melting points and solubilities. Okay? In order for them to dissolve, water has to overcome those ion-ion attractions to dissolve that ionic substance. So size affects this, as does charge. Okay? So we're showing right here, this is the crystal lattice for lithium fluoride. Wish there's a way I can't move it up without turning the light. Let's draw back of this. So this is your crystal lattice for lithium fluoride right here. This is what we call the expanded view, which is not really a good view because there's not that much distance between the particles. They're really close together because they're positives and negatives. Okay? Do you remember from the kinetic molecular theory what solid particles do? Because all particles are in motion unless you're at 0 Kelvin. So what are the particles of a solid doing? They're vibrating in place. And now this kind of shows you why they're only able to vibrate, because they're very close together. They can just, okay? They don't have enough room. Yeah, no, they're stuck in place. Okay? Lattice energy is represented by a modified version of Coulomb's law, where K is a proportionality constant. Okay? That's hard to say. Try that 3 times fast.
Proportionality.
Say it 3 times fast.
Proportionality.
No, you have to say proportionality constant 3 times fast.
Okay.
Fast.
Proportionality constant.
See? Told you. Told you. It's hard. I wonder how many words I say a day when I lecture for all. Try saying what? I can't. Oh, toy boat. I didn't understand what you were saying 1 time slow. Toy boat. Okay, we digress. Let's move back. Okay, hi Landon, when you listen to this, we kind of got a little off track.
Hi, Landon.
Everybody say hi to Landon. Okay, let's get to covalent bonding, because honestly, a large portion of the bonding unit is about covalent bonding, because that's where molecular geometry and molecular polarity comes in. First of all, do Lewis is there a molecular structure for ionic compounds? No. Why?
Because they're just giving those electron away.
They don't have molecules, right?
Oh, yeah.
Ah, yeah, we don't call them molecules. Do you remember what we do call ionic compounds? If you were in my class, I told you not to abbreviate what they're called by their initials. Formula units. Remember I said don't use their initials. Now do you remember? Okay. So most compounds are covalently bonded. Why? The majority of the compounds in the world are covalently
Okay, because
Because they want, yeah.
Nah, there's something that they all have that makes them covalent. Everything has electrons, Mackenzie. What does all living thing contain?
What the?
water. Wait, water.
Elemental. What does all living things? Carbon. And what do carbon do? They only share their electrons, right? So that's why there's so many covalent compounds in the world, because of carbon. Okay? Carbons. How we figure things out, their age based on carbon dating. You know, that
I
kind
don't
of.
think we use carbon dating anymore.
They still use carbon dating sometimes. Okay. All right. So now that brings us to a new model, which is the localized electron bonding model, which assumes that the molecules bound together share electrons using the atomic orbitals, okay, which is what you're used to. Electron pairs are assumed to be localized on that particular atom. We call them lone pairs. Sometimes they're called, what are they called sometimes? I just forgot. Unshared pairs, but I like lone pairs better, okay? This is where Lewis structures come in, describing that arrangement. The geometry is predicted with VSEPR. Do you remember that from Chem 1? VSEPR, valence shell electron pair repulsion is what that stands for. It's VSEPR theory. That's where we get our linear, our bends, trigonal planar, trigonal pyramidal, all those fun words. Okay? The description is blended orbitals, which we'll get to hybrids here in a day or so. Hybrids, remember, is where you're actually blending of the orbitals and mixing them. We didn't really talk about hybrids in Chem 1. If you did the molecular geometry project, you had to, if you picked one of the bonus molecules, you had to do the hybridization. You just wrote it down. You didn't understand what it was, did you? You just looked it up and said, sp3. We're going to learn what sp3 actually means. Okay? So remember, we're following the octet rule, which is stating what? Everybody is trying to get to 8, so that's why they behave the way they do. So when we're drawing a Lewis structure, unless it's less than carbon, we have to make sure that the atoms at least have their 8, except for hydrogen, right? We're going to use a lot of hydrogen. Should you ever give hydrogen anything other than a single bond? No. If you ever give hydrogen a double or a triple bond, it is required that you slap yourself.
What?
Okay? And hard. Okay? Only one electron to share can only form one bond. Okay? If you recall, we can have single bonds and we can have double and triple bonds. Okay? There are only a few things that can double and triple, and they are right here. Synapse. That's a way you can remember what does that. Synapse. Okay? Carbon and nitrogen are the only ones that can triple. Okay? Oxygen in rare cases can, in the case of carbon monoxide. Okay? When you have a single bond, this is going to be a new concept for you. When you have a single bond, it's called a sigma bond. A sigma bond. We're going to learn more about that in a minute, but this is an important concept because they like to put questions on a test and go, how many sigma bonds and how many pi bonds are there? Okay? So, sigma is a single bond. S for sigma. Single. Pi is if you have a double, and if you have a single, if you have a triple, you got a 1 sigma, 2 pi. Okay? So I always tell kids, you got a sigma before you can pi. You got to have a sigma before you can have a pi. Okay? Sigma before you can pi. Okay? We're going to get into that, what it is later. Just know that if you have a single bond at sigma, little lowercase sigma, And if you have a double, then you have a sigma and a pi. And if you have a triple, you got a sigma and 2 pi's.
Why'd they use those just?
I don't know why. I can't answer that question. Okay? So here's something you got to remember. If you have a double or a triple bond, they're obviously stronger than a single bond. Okay? So together they're stronger, but individually a sigma bond is stronger than just a pi. But you can't just have a pi by itself, so it doesn't really matter that much, right? But if you're ever asked, sigma is stronger than pi, but you can never have a pi by itself. Okay? The multiple bonds are increasing that electron density. Therefore, they decrease the repulsions, so they're stronger. They're shorter and stronger. Triple or double bonds are shorter and stronger. So write that down somewhere, shorter and stronger. Obviously, triple are the shortest and the strongest. Okay? Coordinate covalent bonds are basically coordinate complexes or things that you wouldn't think happens, but they do. Basically, hydrogen's getting something for nothing in this case, because hydrogen doesn't have an electron to share, but this little ammonia says, hey, I got 2 extra, I'll share with you. Okay? So, because it's nice. I just...
No, I thought we weren't doing the.
I didn't say I couldn't say it. I said you can't write it. There's a difference. Because sometimes the analogies help you understand it, and then you can explain it. But we can talk in these terms. You just can't write it on the AP exam. Well, then close your ears when I say it. Okay? We know that nitrogen is sharing its lone pair with the hydrogen. Remember, hydrogen has no electrons to contribute. Okay? But all 4 bonds actually end up being identical in length and strength. Okay, here's some we talked about this already. The exceptions to the octet rule. We already talked about this earlier. Fewer than 8. Anything less than carbon is going to have less than 8. Some things can have an expanded octet, okay, because they have d orbitals available to them. Here's what you need to remember. Anything that is in the 3rd period or greater can expand its octet because they have some d orbitals. So even if it's in period 3, like phosphorus and sulfur, they have a 3d orbital available. It just doesn't show up yet, but it's available, so they can expand their octet. So that's why you can get things like PCl5, which looks like this. Attach 5 chlorines to it. Okay? And it has more than 8 around it because it's able to expand. But this is what you need to remember, that it's anything in the 3rd period or higher. So could nitrogen do that? No, nitrogen can't have more than 8. Okay. The ones that really like to do it are chlorine sometimes will, but phosphorus and sulfur are kind of famous for it. They're in the element Hall of Fame. It's not an element Hall of Fame, I'm kidding. Okay. Occasionally you can have a few compounds that have odd number of valence electrons and thus cannot obey the octet rule. Here are some examples of that. There are always exceptions, right? That's what makes chemistry so interesting and fun. I am not feeling your enthusiasm. I'm kind of hurt. Okay, now let's get to how we draw Lewis structures. And if we had looked ahead in our notes like I asked you to, it's right there. Okay? It's right there. Okay? First thing, hydrogen is always terminal atom. Because why? It can only make one bond. So it's always going to be on the end. Okay? And that's one of the few times we say always. we don't like to say always in chemistry because there are so many exceptions, but it always will be the terminal atom. The lowest electronegative atom is going to be your central atom in a molecule. Okay? There is an exception to that as well. Want to know what it is? Carbon. And that's just because usually when it's with hydrogen, hydrogen can't ever be your central. Okay? Then you find the total number of valence electrons just by adding them up. Okay, were y'all at least able to do that today on your quiz? Okay, that's good. So you got half. Okay. You messed one up? I'm so sorry. Okay? Then, this is something we didn't do this is something we didn't do in Chem 1, because it says, on this next one, divide by 2 to get the total number of electron pairs. When they mean pairs, this is probably why we didn't do it in Chem 1. When they mean pairs, they don't just mean bonds. They mean total number of electron pairs together, lone pairs and bonded pairs. So we didn't do that part in Chem 1. I think it would have confused a lot of the students. Remember, for ions, if it's an ion that's negative, what do you have to do? No, add electrons, like for total electron count. Okay? And if it's positive, we got to take them out. Okay? That is y'all's bell.
Isn't it just,
Okay? So we're going to stop here.
wait, isn't it just easier